All right, so let's finish up with Chapter 6. This is a problem we didn't get to go over in class, and it's pretty important because we're thinking about the difference between the force of friction when something doesn't move and the force of friction when it is moving. So we're told that this guy is going to push this 20 kilogram crate, and we know the coefficient of static friction and the coefficient of kinetic friction. Now, based on that, when we think of the force of static friction, the force of static friction has a maximum value that's equal to the coefficient of static friction times the normal force. And we're going to calculate that. So it's 0.7 times 20 times 9.8, which is 137.2 newtons. Now, I was a little bit fast in doing this, but if we look at the forces in the y direction, we see that there's only normal force in the weight, and so the normal force is equal to the weight, which would just be mg. Now, what we learn is the force of static friction is going to be anything less than or equal to this maximum value, but I wanted to find out what it is. The reason being is that when you apply a force to an object and you have static friction working against that force, the force of static friction adjusts. It only has to be just big enough in order to prevent the motion. So in the case where the man pushes with a force of 20 newtons, when we're looking at the crate, we have the push in this direction, and we have the force of static friction in the other direction. And so the reason I know it's static friction is because the maximum value that static friction can have is 137 newtons. Because P is much less than the maximum force, I know that this is a scenario where no motion is going to take place. Now, it doesn't mean that the force of static friction is 137 newtons. If we did that, that would give us a net force to the left, because 20 is much less than 137. We know, though, what's going to happen here is there's not going to be any motion. It's going to remain in equilibrium. And so the force of static friction is subtracted from the force he pushes with to add up to be 0, which means that the force of static friction in this case is equal to the push, which is 20 newtons. Again, keep in mind that the force of static friction only has to be big enough in order to keep the motion from happening. If we look at P equal to 30 newtons, the same thing is going to happen. The force of static friction in this case will be equal to P, which will be equal to 30 newtons. And then even P equal to 120 newtons, P minus force of static friction is still equal. The force of static friction is equal to P is equal to 120 newtons. Now, I was able to do those two cases really quickly because I knew that the push, the P, was still less than the maximum force of static friction. But when I look at the last choice, 180 newtons, 180 newtons is much greater than the maximum static friction. So we're going to get motion in this case, which means when we look at forces in the x direction, we're going to have P minus the force of kinetic friction, and that'll give us the mass times the acceleration. And so this force of kinetic friction is going to be the coefficient of kinetic friction times the normal force, which is still equal to mg, which is going to be equal to 117.6 newtons. And so that's the force of friction for the last case. You can see in that case, of course, as we might expect, that the force that he pushes with is exceeding the force of kinetic friction because we know that there is motion and there's going to be an acceleration. I had a couple slides with that. Okay. Now, here's a situation with the inclined plane. The inclined plane, remember that our approaches that we have, the x-axis is parallel to the top of the incline, and the y-axis then is perpendicular to it. So we're still going to remember that the force of friction is going to be mu sub k times the normal force. And that's because the guy is sliding down the slope. We know he's moving. Now, how are we going to find the normal force? If you look at this picture right here, you can see that the normal force is not directly aligned with the weight. So we look at the forces in the y direction, which add up to be 0 because the man is not moving in this direction. He's not moving up and down along the y-axis. We have the normal force minus the y component of the weight adds up to be 0. Normal force is equal to the y component of the weight, which is the weight times the cosine of 25 degrees. Now, that should look familiar. We've looked at the components of weight earlier today, and so hopefully you are seeing where we get those expressions for the x and y components of the weight. Now, if I want to express the force of friction now, I say it's the coefficient of friction times the normal. I just found out the normal is this, so it's the coefficient of kinetic friction times the weight times the cosine of 25 degrees. And that is how we're going to express the force of friction. Okay, so I have a brick resting on a rough incline. The force of friction acting on the brick along the incline, well, we want to compare it to the weight of the brick. So let's look at the forces that are acting on this brick. I have the normal force, I have the weight, and then because it's at rest, the force of friction is going to be up the incline because of the fact that the direction of impending motion would be for the block to slide down the incline. So the frictional force is going to oppose this, which means that it's up the incline. Now, what is going to be how am I going to relate the force to the weight? Now, if I look, the frictional force is a force in the x direction. And if the block is at rest, my forces in the x direction add up to be 0. And also, we have So, all right, so here we have the pendulum has a bob with mass m, swings back and forth. At the low point, the tension in the string is 3/2 mg. What's the speed of the bob at this point? Again, because this is moving as part of a circle, we know that it actually is centripetal force again. So the two forces acting on the bob at the bottom are tension and mg. We'll look at the forces in the radial direction. Tension minus mg is equal to mv squared over r. All right, so we're told that the tension is 3/2 mg, so we have 3/2 mg minus mg is equal to mv squared over r. So this gives us 1/2 mg is equal to mv squared over r. V squared is equal to rg over 2. So v would be equal to square root of gr over 2. Our r is equal to L in this case, and so the answer that corresponds here is this one. Okay, and this is going to be the last one we're going to look at. We have forces here. We have the tension acting on this bob and the force down, mg. Now, in this case, we could sort of think of our axes looking like this. This one is in the radial direction, and this one is just really y. And really, if we want to figure out how the tension compares to the weight, we could sort of just look at forces in the y direction. And if it's moving in this horizontal circle, as it traces out a cone, those forces are going to add up to be 0. And so this is going to be beta as well. We get t cosine beta minus mg is equal to 0. So t is equal to mg divided by the cosine of beta. And so this is actually going to mean that t is going to be greater than mg. And so that becomes our answer. Because of the fact that cosine is some number less than or equal to 1, it's clearly not 1 because the angle is not 0. All right, and that's where we're going to stop.